Right. Welcome everyone to the second lecture. So today we're gonna tackle essentially two somewhat different areas. First off, we're gonna pick up from where we left off last week and actually go through the Schnorr Protocol, and also talk about the various ways that modern ZK systems utilize a CRS setup. And the idea behind that is that the more efficient the system, as a general rule, the more complex the CRS it uses. So even though we're not really going to go very deep into the details, we're just going to cover the very basics, in that we have protocols that accept a transparent setup that needs no trust, a setup that needs trust to be separate over multiple people, but can be done in one phase, and protocols that need a two-phase setup. Past that, in the second half, we're actually going to cover the first quote-unquote real application of ZK that we're going to see, which is tornado cache. So that's going to be quite interesting, and it's probably going to help getting all those concepts from theory into practice and looking at what actual people are using zero knowledge for in real life applications. So theory first and application second. Let's get started with theory, I guess. Right, so getting back into our theory mindset, we have Schnorr Protocol, and here, suppose, and these concepts might be foreign to you. We'll do a very quick introduction right afterwards. Suppose we have a prime order group that is generated by some generator called capital G. And we want to prove a statement that says, I know of a witness W such that element Y equals G to the power of W. So in this example, our statement is Y, our witness is W, and the relation we're claiming we know an instance of is a relation between X and W that says that G to the power of W equals X. And as I mentioned, people might or might not know what's a group. So a group is a mathematical construct that is very, very heavily used in zero knowledge cryptography. We're going to go through groups in a very quick way. We're not going to cover everything, but we're going to do essentially the bare minimum, if that, so that the protocol makes sense. So groups are collections of objects that have a single operation between them. And for this talk, we'll call that operation multiplication. So if we have two elements, A and B, we can multiply them together and we can produce a new element that is A times B. Now, a group will always come with an identity element, and the identity element in multiplication behaves in the same way as the number 1 does in multiplication. So A times the identity is still A, and the identity times A is also the identity. Now, since we have multiplication, we can also have exponentiation. So A raised to the power of 5 is simply A multiplied by itself 5 times. And for convenience, we define A to the power of 0 to be the identity. Now, what does it mean for some element to be a generator? It means that if we raise it to the right power, it can give us, yes, this is a typo. So somebody pointed out that identity times A is actual A. So this part needs fixing, and it will be after the course. So this is actually A. This is still the identity. So what G is a generator means is that for any element, there is such a power in which we can raise G so that we can produce that element. Essentially, this X is what we call the discrete log of A with regards to G. Now, what we mean when we say that a group has an order Q, it means that this group has exactly Q different objects. And for technical reasons, we want Q to be a prime number. So if we have exactly Q objects in our group, what happens if we raise some element or the generator to some power that is greater than Q? Well, what happens is that we get one of those existing elements. So G to the 1 is G, G squared is some different element, G cubed is another element. And at some point, once we get past Q, the elements wrap around. And this wrapping around creates some very interesting structures and very interesting math within the group. So this was the one-page introduction to groups. Even with this, we can make sense of what is one of the most famous problems in cryptography, and it's one of the problems that powers a lot of the constructions that we actually use in practice. And that's called the discrete log problem. So if we're given a group element and some power, raising G to that power is more or less easy. It's not trivial because there's plenty of multiplications to be done, even if we do something more efficient like square and multiply. So if we know G and X, we can find Y equals G to the X reasonably easily. However, if we are given Y and we are told that Y is G to the X and given G, finding X is extremely hard. Actually, we consider that to be so hard in the groups that we use, in that we base the security around this. So security arguments usually go in the way of, well, if this bad thing was possible, then we would be able to easily produce discrete logs. And we believe discrete logs are difficult to produce, so this bad thing almost never happens. So back to the Schnorr protocol. So the Schnorr protocol tells us what? It tells us that in some way, we actually know the discrete log of some element. Now, we just said that given a random element, finding the discrete log is extremely hard or presumed to be infeasible. So how do we know this discrete log of Y that we're claiming? Well, the simplest explanation is that we created Y ourselves. So in a very simple example, Y can be our public key and the witness W can be our secret key. And as you might know, we can actually create a signature scheme out of this. So given a random public key, finding out the secret key is presumed infeasible because of the discrete log problem. But if you are the one who created the public key, then it stands to reason that you actually know what the secret key is. So how do we prove to somebody that we know the discrete log of Y with regards to G? Well, first off, the prover creates essentially a random element called A that is essentially G to some random power. And this serves to randomize the protocol. And in the end, we'll see that this random value T is what protects our secret W. So the prover will send this blinder A to the verifier. And the verifier at this point has a very easy job. The verifier will simply pick a random challenge C from 0 to Q-1. So the verifier picks a random challenge, and then the prover will calculate what the correct answer is. And the correct answer will be C times the witness plus T. So if this T was 0, then what the prover would be calculating would be C times the witness. And essentially by division, the verifier would be able to get the value of W out, which would not do because that would actually reveal the witness to everyone, right? But since there is this value of T involved, this S does depend on the witness and challenge, but there is also this additional component that helps to essentially blind the witness. So the prover is happy to send this solution S, and now the verifier will check if G to the power of S is equal to Y to the value of C times A. And at this point, we can think of the standard questions where, when analyzing a protocol, is this correct? Is this sound? Is this knowledge sound? Is it zero knowledge? And is there something we can do about all of this interaction? So the way we looked at this protocol, it takes 3 rounds to work. So first the prover sends a message, then the verifier sends a message, then the prover sends another message. So that sounds complicated and expensive, and we would very, very much like to do this all in one step. So first off, any questions? Okay, so let's start with correctness. So what we said the prover is supposed to do is, knowing the witness, they multiply the witness by the challenge they got, they add the blinder T, and they send that to the verifier. So what the verifier does is they check if G to the S is actually Y to the C times A. And it just so happens that this actually evaluates the same thing. So G raised to this entire power is actually G to the C times W times G to the T, and G to the T equals A by definition. G to the C times W is G to the W and the lot raised to C. G to the W is, as we assumed, Y. So this does work if everybody does what they promised to do. Now, what is interesting is what happens if people try and cheat. So we're gonna mostly fast forward through the proof because the idea is to get some intuition about how these proofs work and how we use those 2 worlds that we talked of in the previous lecture, where we have the world in the proof, where we have additional powers or we are able to cheat in some way, and we have the real world where these additional powers go away and we're left with a real protocol. Soundness in Schnorr's protocol is actually almost always true. So we said that G is a generator of the group, which means that if Y is in the group, G will generate it. So there is some power where we can raise G to produce Y. What we really want to know is not if G generates Y or not. It's if the prover knows what that value is. So if Y is in the group, this W we're talking about must exist. The question is, does the prover know it? So for that, we don't care about soundness, we need knowledge soundness. And for knowledge soundness, the argument we make is this. It's that either the prover is not really good at cheating at the protocol. Or if the prover is good at cheating at the protocol, then they might as well know the witness. This is how the argument goes. And by extension to that argument, we get that, well, if the only people who are able to cheat successfully might as well know the witness, then there's really no cheating going on, because the only people who would be able to cheat would also be able to legitimately calculate a witness. So to see that, we're going to go through a thought experiment. And let's say that we can force a prover to answer twice, and specifically, we can force them to answer twice for two very specific challenges. So we set those two challenges to be 0 and 1. So it just so happens that if the verification works, in the first case where the challenge is 0, we will have that g to the s, where s is whatever the prover provided, must be equal to y to the challenge times a, because that is what the verifier is checking. So if the prover can actually win when the challenge is 0, then the prover is able to provide a solution s such that this equation is true. So what this means is that g to the s is a, which means that we know the value t that went into making a. So we know that a is actually g to the s. Now for the second run, we have changed the challenge from c equals 0 to c prime equals 1, and the prover will probably give us some new solution s prime, such that g to the s prime is y to the new challenge, which is 1 times a. So what we get is that g to the s prime equals to y times a. And simply replacing y by g to the w and a by g to the t, we get that s prime here actually. G to the s prime is g to the w plus t, which means that s prime is w plus t. So knowing that s prime is w plus t and t equals s, we learned that the witness we were after is actually w equals s prime minus s. So what does this mean? It means that if somebody was prepared to correctly answer for those two challenge values, then they could also get a pen and paper and find out the witness. So there can be no cheating by people who can answer those two challenges. Well, you can say this is overly specific. Maybe they can cheat by answering other challenges, right? Well, not really. So suppose we change this argument around and we argue that if somebody can correctly answer some challenge C and some other challenge, which is C plus 1, then we can use a modified version of the same argument and then get the witness. Can we do that? Yes, we can. So now it's getting even harder to cheat, because essentially anybody who can answer two successive challenges must know the witness, ergo they cannot cheat. And if we play around with the math a bit more, we could actually change this technique we saw so that if a prover can answer any challenge C and any other challenge that is not C plus 1, now it's C plus A, where A is some arbitrary value, then we can still use a calculation to get the witness. Then what that means? Well, then that means that anybody who can answer two different challenges has a way to produce the witness. And that means they cannot be cheating. Because cheating means that you can solve the protocol without knowing the witness. But if you can answer 2 out of Q different questions, then you know the witness. So you should be able to pass the protocol. So the only possibility for somebody to actually cheat in this way is if they can only answer 1 out of Q questions right. But in the groups we used, Q is huge. Q is in the order of 2 to the 256. So that happens almost never. And this is how the security argument is structured. So we don't directly argue that, well, people cannot cheat. We argue that if people could cheat, then they could also produce XYZ, which either means that they were not cheating in the first place, or it means that some very hard computational problem then becomes easy, which is something that we don't believe is true. So this kind of cheating prover cannot exist. Does this make sense, at least at a high level? Okay, so is it possible to modify the protocol to require more than 2 correct answers? Not in a way that immediately makes sense. So what would happen if we had this this baked into the protocol? So suppose we go back here and instead of picking a random C, we pick a random C1 and a random C2, and then we have S1 and we have S2, and then we check twice. Well, C1, C2, let's say. Well, what would happen then? So for this example, I'm using the same value of A, and we have the verifier pick 2 challenges. The prover then print out 2 solutions, and the verifier will do 2 checks. So that would actually fall in this strange thought experiment world in which we are allowed to ask 2 questions in a one question protocol into the real world. And this protocol would now be insecure in that it would enable anyone to carry out essentially this calculation here, or the modified version of this calculation, and extract the witness. So this protocol would be secure in the way that people could not cheat, but it would not be zero knowledge because it would actually be leaking the witness. So again, we get into this question of whether it's fair to make the prover answer twice. And inside the thought experiment of a proof, it is fair to make the prover answer twice, because if the prover has is just playing games by himself, or if the prover is able to answer twice, then he's also able to carry out this extraction process we described. But the protocol does not force him to answer twice, because if he did answer twice, then the verifier could actually get the secret. So there's a delicate balance between whether the prover can answer twice and whether the prover should answer twice. And the argument we're making is that, well, the protocol only asks him to answer once, but if there is only one possible question out of 2 to the 256 that he can answer, then he almost never wins. And then we argue that if there are at least 2 ways in which we can answer successfully, then he could essentially calculate the witness from himself. The other way we can think about this is that the prover can be some executable that we can run in a virtual machine. And in a virtual machine, we can start the prover, get to some point, save the state of the virtual machine, go forward a few steps, then rewind, then go forward again, and get the prover to do some extra work without him realizing it. Now, for zero knowledge, we have a very different goal, which is to try and simulate the protocol without knowing the witness. And this seems hard because I was just telling you that we cannot get the witness by just knowing G and Y. And since we're not giving it, there's pretty much no hope of us getting the witness. But we can produce a faked version of the protocol that looks the same as a real one without ever using X. And for that, the process is extremely simple. We will pick a random challenge and a random answer by the prover, just random numbers between 0 and q-1. And then we will set A to be the only value that makes sense. And the only value that makes sense is the one that works in the verification equation. So flipping things around, we had G to the S equals A times Y times C. Flipping this around, we get A equals G to the S times Y to the Q minus C. And this is essentially a fancy way of saying minus C. And we have faked the protocol. We have faked the protocol. Why? Well, first off, because the values we picked make the verification equation check out. And this is because we picked the one value of A that actually makes it work out. And the other thing that takes some extra math to work through is that the fake logs look the same as real ones. Why do they look the same as real ones? Well, what does the challenge look like in a real log? Well, it looks like a random value C, right? So if in the fake log we create C by picking a random number, and the real log we create C by picking a random number, then they look the same. Now for S, it's less easy to see that the distribution is the same. But essentially, what we have here is that this T is random, and this T is entered into here. So we can argue that this T value effectively completely randomizes S. So it's fair to say that in the real protocol, S and C are uniformly random elements. And if S and C are uniformly random in both the real world and the simulation, and A is the only value that works, then the real protocols and the fake ones look the same. I'm glossing over a bit of statistics here, but it's nothing we need directly. So how could this be? Well, this is because we cheated. It's because we did things in the wrong order. In the actual protocol, A is revealed before C is ever calculated. So in the real world, you cannot create A based on C before seeing C, right? So if you are playing this protocol for real, this does not work because these things do not happen in this order. But if you are simply tasked with coming up with a log of the protocol after the fact, then you can just simulate the events in any order. And what does this mean? This means that the protocol is secure when it's performed live and you're choosing the challenge, and that the logs are useless if somebody just shows them to you or if they just pass through your screen without you controlling the challenge. So back to last week's question about extraction and zero knowledge. So we have knowledge extraction saying that we can get the witness. We have zero knowledge saying that we can fake the protocol with no witness. Who is right? They are both essentially hypothetical worlds. In one world, we're able to cheat by asking multiple questions or by knowing some additional feature. And in the other world, we are able to cheat by doing things in the wrong order. Whereas in the real world, neither option is actually available to any of us. So in the real world, we are not able to cheat and create proofs without knowing the witness. And on the other hand, we are not able to get the witness out of a proof. Now, however, there is a small gap in that in some ways, the real world might end up looking like this simulated world where we are able to cheat. And this happens with protocols that might have trapdoors. So protocols that are very efficient, like Groth16, have what's called a common reference string. And this is a structured file that contains group elements that have some very particular relations. And for any such common reference string, there is a related trapdoor that enables one to create fake proofs for that common reference string. And essentially, in the research paper, that is how we are able to prove zero knowledge. We say that, well, if we are able to bring our own common reference string, then we are allowed to know the relevant trapdoor, and we can create fake proofs. And that's why the protocol has the zero knowledge property. Because if the bad guys did not create the CRS, then maybe we're able to use the trapdoor and create fake proofs. So in their eyes, proofs are zero knowledge. On the flip side, when we are arguing about soundness, we argue that, well, the bad guys did not create the CRS, so they don't know what's in it, so they cannot fake proofs. So our argument about security actually goes through. So what happens in the real world? And this is the more relevant question. So clearly, the one thing that we absolutely need to ensure in the real world is that the bad guys have not created the CRS and that they have no access to the trapdoor, right? Because if the bad guys are able to just bring their CRS from home, then that CRS will probably be trapdoored. The bad guys will know the trapdoor, and we lose. Questions up to here? Okay, moving on. So suppose we have this extreme simplification of a CRS, and this CRS simply consists of one single element. So it's an element that looks like G to the A, so it's the generator raised to some random power. Now the trapdoor, which is essentially a description of all the information that went into the CRS is a single element alpha. So what we want to do is we want to create some element that is G to some power alpha without the bad guys knowing what that power alpha is. So one way to do that is to essentially have, let's say, me create the CRS. I will pick my own alpha. I will publish G to the alpha without giving you alpha, and nobody will know alpha, right? So is that secure? Okay, somebody says that this is not secure. I'm deeply offended. Please explain why. Right, so you don't really know me. So if I tell you that I just created G to the alpha, I published G to the alpha, but I'm going to throw alpha away and not tell anyone, you have no reason to trust me. I know the trapdoor. So I could cheat and create proofs that are not true, or proofs that I should not be able to. So what we would like is a way to get an element whose discrete log nobody knows. And there is actually a simple way to do that without getting into fancy protocols. So what we can try and do is get some random looking data that is above suspicion. And that could be stock market closing prices, newspaper headlines, various temperature readings around the world, and hash them to get essentially some coordinates. And by those coordinates, we can determine an element in the group, let's say capital A. Now, this capital A will be equal to G to the alpha for some alpha. But nobody actually came up with this alpha. It's unknown because we directly hashed into the group to get capital A. So we picked a random element without going through its discrete log. So at this point, we don't know the discrete log, and this element actually works for us. So this actually works, and this is actually something that is being put to use for a lot of CRSs, but it can only get us so far. So this is what's called a transparent setup, because it does not need multiple parties, and the only quote unquote trusted part is in the selection of the random data. So if people are careful about specifying what the data to be used is going to be ahead of time, then you can probably rule out that they had the influence in actually fixing that data. And past that, you can believe that the elements that we came up with have an unknown discrete log. And by extension, that nobody knows the trapdoor. So this can be used to create the CRS we need for protocols such as bulletproofs. And this is quite efficient because it only takes one person to specify what the data to be hashed is going to be. And then you can essentially create as many elements as you need. Because this is obviously a toy example that uses just a single element, but it's the same to you produce one to as it is to produce 1,000 or 1,000,000 elements. You just hash multiple times. Right, so let's look at something that's slightly more involved. And this would be a common reference string that looks like what, say, Plonk or Sonic uses. So here we have moved up to common reference string that uses, well, 2 elements. But it's not any 2 elements. It's 2 elements that are related in a particular way. So the first element, let's call it A, has discrete log A. And the second element, let's call it B, has discrete log A squared. So our previous trick would not work. Our previous trick would give us 2 random elements with discrete logs, say A and B, but it could not give us this particular relation where the discrete log of one is exactly the square of the other. And before we go into the tough solutions, just trying to multiply this by itself does not produce what we need, because g to the a times g to the a is g times to the 2a, not to the a squared. So this is actually non-trivial to produce, and we will need to use multiple players to build something that has this structure. And this is where all this talk about updatable reference strings or snark ceremonies comes into play. So we're going to go through a basic example where 2 players will cooperate to build a reference string of this structure. And obviously this generalizes into many more players. So we have everybody's famous crypto people, Alice and Bob. So Alice will pick a random number, which is A. Bob will pick B. And Alice will start by building her version of the reference string, which is g to the a and then g to the a squared, which has the structure that we require, right? So the discrete log of the second element is the square of the discrete log of the first. So this is fine. But at this point, Alice knows A, right? But then we pass this off to Bob. So Bob takes Alice's reference string, which is XA, YA. He creates his own random value, which is B, and he raises the first part to the power of B, and the second part to the power of B squared. This actually should be YA to B squared. So what happens now is that the reference string still has the structure we require, because working out the math, we have that this is g to the a times b, and this is g to the a squared times b squared. So this looks like a valid reference string. And what we're hoping for, and what we can actually believe, at least at this level, is that since Alice only knows A, she does not know A times B, and since Bob only knows B, he does not know A times B, and same for their square. So great, we have something that ensures that neither player knows what the secret is unless they cheat. And at this point, this protocol does not prevent cheating. So how can people cheat? Well, Bob is supposed to take Alice's reference string and just multiply by B or raise to the B and raise to B squared. But what he could do is simply throw everything away and just replace what Alice gave him with something that is completely under his control. And then he would know the secret. So Bob is allowed to cheat, and also Alice is allowed to cheat. Alice is allowed to cheat because she's supposed to take 2 elements where the second has a discrete log of the square of the first, but she might do something else. So both people have the opportunity to cheat. If they could not cheat, then this protocol would be fine. So let's prevent that. So far the protocol looks the same, but also Alice will also attach a proof that she knows how these two elements got made and that she knows that they have the correct structure. And this will also be the case for Bob. So they will perform the work they're supposed to and also produce a proof that says that they performed the work they were supposed to. So what would that proof look like? Well, each of them in the very base case would essentially have to prove three things. They would prove to know the log of their first element relative to the base. They would want to prove that they know the log of the second element relative to the base, and we will call those values W and Z. And they would also need to prove that Z is the square of W. And well, these two instances look very similar to Schnorr. So even though in actual real-life protocols, the security level we're after is slightly more complicated and we actually don't end up using Schnorr, this is the form of things that Schnorr could prove for us. So it's quite close to something that we can use in practice. Now, proving that the structure is correct could also be done with a modification to such a protocol, but in concrete cases, it can be checked directly. So we actually are able to skip this part and check it at the end. So this is the way that we can build an what's called an updatable setup, like the one in Plonk. And the reason why it's called an updatable setup is that if we are at the point where Bob has just finished his work and he has created his reference string XBYB, then without any assistance from Bob or Alice, Carol can come in and she can create her own update to this reference string and her own proof about that, all on her own. So she can produce an update without needing to coordinate or cooperate with the previous CRS builders. And this is a very valuable property because it cuts down on the amount of setup, and it means that the CRS can be improved and made even more secure, even if some of the original parties have dropped out. This is a very valuable property. On the other hand, moving to our final toy example of today, we might have some CRS that has a structure that is even more complex. So we have A squared, and now we have a third element, which is A plus A squared times another secret multiplier, which is gamma. And now our previous protocol fails because Bob cannot update this term. Why is that? Because, well, if Bob starts with G to the A and G to the A squared, then he knows that all he needs to do is raise the first element to the power of B and the second element to the power of B squared. So this is fine for Bob. But Bob has no idea what he's supposed to do with this element. So here he raises element to the power of B, here he raises element to the power of B squared. Should he try and raise this element to the power of B? But then this term would be correct, but this would only have B to the power of 1 rather than B squared. If he raises the entire lot to B squared, then this would be B squared, this would be B squared, this part would be correct, and this part would not. So it's very hard for Bob to know what he's supposed to do because all these terms are mixed here. and he's not able to do one simple operation that will produce a randomized version of this term. So how do we fix this? The answer is we really don't. So what we do is that we run the previous protocol, but just on the first two elements. So we get g to the a and g to the a squared, and from these we can essentially freeze a version of g to the a plus a squared. So at this point, a is frozen in the eyes of the protocol, and this might be something that was created by involving 2, 3, 5, 100 different players. But at some point, we will freeze those two values, and we will create this frozen version of g to the a plus a squared. And now we will run this protocol anew, but only for this term, to figure out a random value of gamma. So we have this frozen value of g to the a plus a squared, and we will have power people raising to random powers, let's say gamma of Alice, and then gamma of Bob, and then gamma of Carol, in order to randomize this part. So this runs over two phases. And the issue with this is that once we have frozen this value, we can no longer run updates for this. So if we have this first part that was contributed by 3 people, Alice, Bob, and Carol, and then Dave comes along, Dave is not able to pick up from this point because this value will have been preset. So this ring needs to be run once with one set of participants, and then the second step needs to be run again with either the same or a different set of participants. But if somebody comes late to the party, then they can only add randomness into the second part. So a latecomer here can only make this value of gamma, quote unquote, more secure. They are not able to have any influence on the value of alpha. So if for whatever reason they have reason to believe that the randomness that went into alpha is insufficient, then they need to go back into step 1, run the updatable protocol again, create a new frozen value, and then run step 2 from scratch, which obviously creates the problem that you need to track down the original contributors and have them play again, because if you had 100 people running each round and person 101 contributes to the first part, then the second part needs to start from scratch, which means that person 101 needs to find 100 extra people to add randomness, because the randomness that was added in phase 2 should now be discarded. So this is quite complex, but this is the price we pay for very efficient zero-knowledge protocols such as Gross16. So there are some extra parts behind the scene that we're not going to cover. So in the original parts of Tau paper, there is also some additional contribution apart from Alice, Bob, Carol by what's called a random beacon. This was shown to be not strictly necessary, but also not harmful. And for Gross16, things are actually more complicated than I described, because this frozen term is actually dependent on what application we're trying to create a proof system for. So this frozen term for, say, Tornado Cache would be different from the frozen form for, say, Semaphore. So what does this mean? It means that you need to run phase 2 multiple times, which is more trouble and more expensive, but that is what you need for a more efficient protocol. So just going from more to less efficient, or from less to more efficient. Bulletproof, transparent setup, easy to do with a hash function. Plonk, updatable setup, easy to do with a one-phase construction. Growth 16, you need the two-phase construction, and you need to rerun phase 2 for every different proof statement that you want to handle. Okay, this is a good place to take questions, and then we move on to Tornado Cache. Okay, on to the fun part. So, Tornado Cache is a privacy solution for blockchains, and it essentially, at least before the Nova version, solved one of the big two privacy problems on blockchains, which is who's paying whom. The other is how much. So the Nova version of Tornado Cache also addresses the how much question, but what we're looking at today is the base version, which only covers who pays whom. So Tornado Cache offers privacy by doing something very, very simple. It allows you to do two very simple things. Either you deposit money and get a note, or you turn in that note and get your money back. That's it. So the idea is that if you deposit money from one address and you cash in the note from another address, then these two addresses should not be linked. And this is what gives you privacy. Well, all that minus fees, minus gas costs, etc. So this is all that Tornado Cache does, which is still extremely useful, but at least in concept, it's very, very simple. It only does two things. It takes money and gives out notes, or it takes notes and gives out money. The only hard part is doing this properly, right? So before we move on to how we can build our toy version of Tornado Cache, we're going to look at one crypto primitive, and that is hash functions. It's something that you have probably looked at previously. So we can get any amount of data and compress it into a small random looking digest, right? And the properties that they have, at least in crypto context, is that it's very hard to find two different pieces of data that hash into the same output. And also, given the output of a hash function, it is quite hard or infeasible to figure out what the input was. This is very useful to us because in many cases we can use the hash of something in place of something and then reveal it if and when we need to. Okay, so we're gonna try and make Tornado Cache without knowing anything about security and with only knowing how to use hash functions. This is gonna be fun. Okay, so we're gonna create our toy cache application that is going to rival Tornado Cache. And how that's gonna work is that we will start this smart contract that will maintain some list of hashes, and that list is called L, and that starts out empty. So people are able to create nodes by simply selecting any random value they want, let's call it X, they hash it, and they hash it to some value they will call C. Now, how they deposit money to Toy Cache, they will send one F and the node of their choice to our smart contract. The contract will happily take their one F, and they will store the node they provided into the list, into the first available position. And at least for this talk, we're only going to handle the case where the currency amount is fixed to one F. We're going to talk about variants of that later, but in the simple case, we're not trying to hide the amount of value. We're only hiding who pays whom. Okay, so how do withdrawals work? Well, the simple case is that you send your secret value X to the contract and you say, well, I have this note that opens position L. And the contract will check that the value X you said is actually the same as what is stored in position L. And if it is, it will send back your 1F, potentially minus fees. And it's also then going to delete your note from the list, so you cannot double spend it or double cash it in. Or you could do the same thing via some relayer, and the relayer will post another address for you. And this can be done so that it's not obvious who is paying for the gas for the smart contract to run. But this is essentially a variation of the first case. So does this work? Have we built Tornado Cache? Right. So good point. This list is public, so there's no privacy. So if you see that when Pyrros sent money to Toy Cache, position 15 was added, and then somebody cashed in position 15, then that somebody was Pyrros. So there's no privacy. Also, this needs quite a bit of storage. Although deleting all hashes can help, still you need essentially one storage. You need to store one hash per, say, customer, or at least per customer who has a deposit with you. But what is the biggest problem with this is front running. Because if I'm sending the secret value in plain text to the contract, then somebody can just pick up that value and send it before me, and then I've lost my money. So Toy Cache does not work. Okay, so now we're going to deploy Toy Cache 2.0 using zero knowledge, right? Surely this will go well. So we will do essentially the same design, but now we will be smarter. We will not send the value of X in the open. We will send a zero knowledge proof pi, such that pi is a gross 16 proof that says this: I know a value X in a position L such that position L in the list is equal to the hash of X. And then the contract will check that pi verifies. And if so, it will send back 1F. So instead of sending X in the open, we will send a zero knowledge proof that we know the correct value of X that opens position L. And in this way, we will have privacy. Now, does this work? Okay, answer from chat. This allows double spending. It does, because at this point, the contract actually never knows what X or what L is. So there is no way for the contract to delete a spent note. There is no such concept. So notes can be spent multiple times, and the proofs do not discount that by any way. So this is a problem. This is clearly a problem. So Toy Cache 2 kind of works. We have fixed a few issues, but we have introduced more. So we have now introduced double spending, which is clearly a problem. We have fixed privacy, and we have probably fixed front running, because we can make this proof actually be address specific. And what this means is that if this proof is sent by our address, it's going to work. But if somebody copy pastes the proof, hoping to send the money to their address, it's not going to work. So that should fix front running for us, right? On the other hand, storage got a bit worse, and it got a bit worse because we no longer know how to delete things off of the list. But we're getting there, right? Essentially, what we need to fix is double spending. Okay, so let's try and fix double spending. So now we're going to hash not one value x, we're going to hash two values, x and y. So we're going to create values c such that they're hashes of random looking values x and y. And again, we deposit by sending one f and the note to the smart contract. The smart contract will store the note in some position. And then when we want to withdraw the note, we're going to send the hash of y. We're going to send this proof pi of groth 16 that we've now slightly modified. So now it says that we know xl and probably y here. Okay, some live additions. And y equals h of y. So now we send hash of y in the open, and we modify the proof accordingly. So now the contract will verify that the proof is correct, and also that hash of y has not been reused. And if it has not been reused, it will add it into some list of spend notes and then send back our 1f. If h of y has reappeared, then it will refuse to hand out any money. And this is how we fix double spending. Essentially, if this value of y is reused, this h of y will appear again. And if this h of y appears twice, the second time, it will appear in the list S, and it will prevent the contract from sending out any money. Now, does this work? It actually does. The main issue is that the storage requirement is quite bad. And not only is the storage requirement bad, but list traversal is actually quite expensive inside of a zero knowledge protocol. So what remains to get this toy cache example from the notes into actual quote unquote production level Tornado cache? Well, using the list for storage is hugely inefficient. And accessing the list is extremely inefficient with groth 16. The reason is that in terms of verification time, adding to the witness in groth 16 is free. Adding to the statement is not. And the public data, which is the list, is part of the statement. So what's the fix? The fix is actually quite simple. Instead of storing the notes that are yet to be spent in a list, we will store them in a Merkle tree. So if we deploy this fix, then we have essentially reached 95% of the functionality of Tornado Cache. The only thing we need to add to that is multiple choices for value. And if we only have a small list of choices, and I think the initial choices were something in the area of 1, 10, 100, a tenth, then we can just essentially run this protocol 4 times independently, and we arrive at the same thing. If we want arbitrary options with different privacy needs, then we need a much different design, which is essentially Tornado Cache Nova. So Merkle trees, I'm actually going to skip for time. It's something that's extremely popular even outside crypto. And the idea with using Merkle trees and snarks is that they allow us to have a very small representation of our data in the statement, which is good because that part is usually expensive, and a reasonably sized representation of the path to our data in the witness, which is also pretty good. Now, when implementing a Merkle tree in a snark, we usually decide to use a hash function that is optimized for use in arithmetic circuits. This is something like MIMS or Poseidon. And you will see that Tornado Cache uses MIMS, I think, for most stuff, as does a semaphore. Here, there's a few tricks that are relevant in ensuring that Merkle tree traversal is slightly more efficient than the naive case. And this mostly has to do with avoiding forks in the calculation. So essentially what you want to do is hash one thing where the value of that one thing depends on things like left, right, 0, 1, or various flags. You do not want to do one hash calculation if the flag is true and one calculation if the flag is false, because this essentially costs double in the circuit. I'm running through this because of time, but this is something that you can also see in your own time. Finally, some pointers for some very related works that you should be able to approach at some level, given what we've covered. Semaphore is probably one of the closest apps to Tornado Cache in terms of design. The functionality it achieves is very, very different, but you will see that the underlying techniques are quite similar. Semaphore has some extra functionality with regard to signing, but apart from that, you can look at it as a slightly more complex version of Tornado Cache. Now, there is also a different technique called one out of many proofs, which was a research paper quite a while ago that achieves a similar result as Tornado Cache. And it does not use snarks or a trusted setup. However, we go back into using a list. So the verifier is much more costly. It's not something that people would be able to deploy in a smart contract. It's something that needs native support from a blockchain. And some blockchains have actually built things based on this design. But it offers a different view into the same problem. Similarly, ZeroCoin also does the same thing. It uses accumulators instead of Merkle trees, but the end result is pretty much the same. A very different approach is Monero. It uses much smaller sets of people for privacy, but it also hides the value. And then we arrive at Zerocache, which hides the value and uses similar Merkle tree based design. So even though Tornado Cache is relatively new and most of these constructions are actually older, it's a very useful prism from which to examine a large number of designs that are out there. Okay, that's what I had from today. So we can take a couple questions and call it a day, I guess.
So there's one question I have that might be a little bit beyond the content of the
Sure.
slides, but So we've been looking a little bit at the actual like GitHub repository for tornado trees. Are you familiar with those at all?
I mostly went over the paper and the audit they had, but ask away and we'll see what happens.
Okay, well, I guess we were just trying to understand how tornado trees are working and if there's any high-level description. But if you haven't gone through the code, I think it wouldn't be a very useful question. So I'll look through more. I'll look through it more after this.
Sure.
After yeah, thank you.
So I should add is a very nice transition because next week we're in for a treat. Roman Semenov, who's co-founder of Tornado Cache, is going to come and give the next class. So we're actually going to exactly dive deeper. I see that his limitation of time and some of this stuff is actually very complicated, like Hunter and I have been looking at the Tornado Trees code ourselves and not fully understanding some of it. But I think next week we'll have it resolved, having the master himself will come here and explain how it works for us. There's a question there.
Anonymity sets. So it's I don't think it's reliable as the only metric. So there was some research into I think Zerocast and Monero, where Zerocast has presumably the gold standard with regards to the anonymity set, and well, Monero just goes for what's practical. And the takeaway was that if not enough people are using the privacy features, and if they're not forced to, the anonymity set by itself might not be enough. Now, if I'll have it posted in the material. So essentially, anonymity set is a good benchmark, but no. So relayers are not the solution to front running. The solution to front running is to bind the proof to the address, and that can be happening both if a relayer is involved or if somebody is just contacting the smart contract directly. Also by not publicly posting the private data, is Toy Cache version 1 did.
This is a very good presentation and really informative again. Thank you very much.
Cheers. Okay. So everybody have a very nice and happy and productive 2022, and take care.
Yeah, thank you so much, Pyrros. It's been wonderful, beautiful way to kick off the course, and thank you very much for doing it for us. And we hope to see you again in the new year too.